Nice background. Okay, so let's start. So, hey guys, hope you all are doing well. So, we are into the seventh talk of the series, and we have had really great and interesting talk sessions by various people, or I'll say students of the institutes, on different paradoxes we observe in astronomy. So, continuing with the theme, now today we have Anirudh Ravishankar from the BSMS 2018 to talk about the missing barium problem. So, I won't take much of the time and I'll hand it over to Anirudh. So, you can go ahead.
Okay, great. Hello, everyone. So, as Swastik mentioned, topic or the paradox I chose for presenting is the missing baryon problem, and it's pretty short. So perhaps it would be nice if you have questions, you can stop me in between so that it will go more towards something similar to a discussion rather than just me presenting. Because honestly, this is very deep into cosmology, and that means I'm not extremely good at it, but I have looked into it enough to be able to present something nice, hopefully. Okay, to start off, so the introduction to the paradox is this. So on the left-hand side, you have this is the cosmic background, microwave background radiation, and I'll explain what this is just in case you don't know. And this is an image of the late universe. So in the early universe, basically, what we have found from cosmological, not just simulations, but also from data from the cosmic microwave background, we have found that the density of baryonic matter is about 4 to 5%. I'll elaborate on this a little ahead. And the late universe, that is in the universe that is close to us, when we look for what the density of the baryonic matter is, we show that there's about 30% missing. That is, we're only able to get 70% of the value we've got from here. So this is the outline of the paradox. That is, in the beginning, you're seeing a lot of a certain amount of baryonic matter, but then when you look at late universe observations, you are not able to find the exact level of baryonic matter we expect. So to start off, simple explanation as to what a baryon is. So here you have the baryons, which are basically protons, neutrons, and a little other stuff, but mostly just protons and neutrons because they're some of the most massive subatomic particles. And for for the present scenario, for the presentation, baryons also refer to electrons, even though officially the electrons are not baryons. But when we're quantifying stellar masses or stuff like that, we still consider all of these electron masses as well, because you have three electrons in space and we quantify those masses as well. And so these masses, these baryons are present everywhere in stars, interstellar dust, planets, uh, basically everywhere. Not all of them are easy to find because stars are luminous, and so you can find them easily. And or some of the other stuff are luminous as well, but dust, planets, and stuff like that are harder to find because they are not luminous objects, and we need a little cooler techniques, if I may say, to find their density contribution. So that's what a baryon is. And so how is baryon distributed in the universe? So in this pie chart, you have this black part, which is basically dark energy, which is about 70%. This is the energy distribution of the universe, and 26% for the dark matter, and only 5% is normal matter. That is, for the sake of this presentation, I'll call baryonic matter. I will not go into much of what this 70% and this 26% means, but basically how we are getting this 5% is based on cosmic abundances. That is, we see a certain amount of level of helium or lithium or certain cosmic abundances, and based on that we say, okay, the number, the baryonic content is probably this much, because if it was heavier, then we would see a lot more heavier atoms like beryllium, boron. You'll see a lot more abundances of those atoms, but we don't. So based on those constraints, we find that the baryonic matter amounts to about 5% of the universe. And within the baryonic matter, there is another thread of located. This is from a paper in 2012. So this is not as recent, but I will explain how this works. So here you have galaxies, which is about only 7% of the whole baryonic content. That is 7% of this blue pie chart uh, above above pie chart. So that is only, it accounts to about only 7%, and the rest is all a lot more complicated and harder to find. If, for example, you have this thing called Lyman Alpha photoionized. So this basically refers to the rest of it all refer to interstellar dust or uh, intergalactic dust. In fact, WHIM refers to warm, hot intergalactic medium, and I'll get into how we find these percentages in a little while. And also in 2012, they saw that about 30% of the baryons were missing. That's what the paradox is. Like, where is this? Where are these 30% supposed to be? Um, yeah, so for the dark matter, dark energy, I'm not going to get into it much, but the brief idea is that they are detected based on the gravitational effects they show. Not enough matter is discovered to explain these gravitational effects. So what is the cosmic microwave background? So this is a map of the cosmic microwave background, and what it actually means is that in cosmology, so what we have is after 300, about 370,000 years after the Big Bang, all the gas has cooled down to a certain extent that electrons and protons can fuse to form hydrogen atoms, neutral hydrogen atoms. So it's the first hydrogen atoms ever formed, and so it's called the epoch of recombination. And the radiation, and so before that, before the epoch of recombination, you have photons as well. You have photons going around that hot, dense gas in the early stages of the Big Bang, but those photons never came out of those gas because the gas was too hot and the mean free path is very low. So the photons basically never came out in that period. But once the protons and electrons started combining and forming hydrogen atoms, these photons were able to escape this opaque component of dense gas. And so the photons that we see in the cosmic microwave background is these photons, which have the first ever photons in a certain way, which we are able to observe. And they are spread out across all parts of the universe. And that's why you have it all across the map. So this one is a 3D map first, but laid out 2D. And here you see that it seems like it is not homogeneous. Like you have a lot of dark patches in red, and you have a lot of blue patches as well. But actually, these are extrapolated in the sense that the actual deviations are very, very less. In fact, if you fit a black body spectrum or how the radiation is for the cosmic microwave background, you'll see that the fit is very, very good, and the fit is at about 2.7 Kelvin. And you see that these error bars are very, very low. And these error bars do exist for a reason, which I'll come into, which I'll come to that. But these variations are so small that in this map does not mean that there are these areas of red or of higher radiation or significantly higher radiation. There are very minor anisotropies or minor fluctuations. Also, since it is about 370,000 years after the Big Bang, these photons are heavily redshifted, and their redshift is about 1,100, and this is the max we can ever go. Like anything above this redshift, we won't be able to get photons because, as I said, any redshift above that, the photons simply did not escape from the dense gas after the Big Bang. And so, since they are so redshifted, we only find them in the microwave part of the spectrum, and hence the name cosmic microwave background. And so, once we have what the CMB radiation is, we can use that radiation to find baryons in the early universe. So, these are values calculated using the Planck telescope, which was, I believe, it's around 2015. And so, what we've done is the anisotropies in the CMB radiation is used to estimate the baryon density. So here in this table, you have the baryon density parameter, omega b, and so you have it as 0.0486, which is what I mentioned earlier, where baryonic matter is about 4 to 5%. That's what the 0.04 is. And you also have a bunch of other parameters, but for now, this is what we're interested in. And this one is found by measuring the anisotropies I mentioned in the previous image. In this image, you have all these red patches are only small fluctuations, but these small fluctuations are used to find the to find this baryon density. And how they're done is honestly it was a bit complex, and they used Fourier transforms, Pareto harmonics. It's pretty complicated, and if someone is interested, I think I can send a few links. But this is the brief idea of how we arrived at the fact that the baryon density at the early universe is 0.0486, or about 4 to 5% baryon density. And also, this correlates with the value obtained using the Big Bang nucleosynthesis model. That is, we have a theoretical model for theoretical basis for all of this, and we also have other observations. And the 0.0486 value is pretty close to what we observe from the Big Bang nucleosynthesis model. So this is very good data, or reliable data. And now, after we have a good idea of how the early universe looked, now we move to the late universe, or what people like to call the low redshift universe. Because of low redshift, the distances to these stars or galaxies are somewhat lesser than the very high distance. Well, basically, the redshift is low, which means the objects are close. And if objects are close, the photons we get are pretty recent, and thus they are late universe objects when we observe them. And when we have to estimate the baryon density for this, for all of this, the finding baryon density of baryon density contributions from luminous matter is pretty straightforward. Like you have a lot of stars and stellar clusters, and what you do is you find their masses and their luminosities, and using that information, we can estimate their contribution, and that part is a bit straightforward. But what is harder is to find how the baryon density is estimated for dust, interstellar dust, or dust present between galaxies and stuff like that, which is called circumgalactic medium, galactic halos, intergalactic region. So these techniques are not very straightforward, and I will get into this. And so what is the logic behind comparing these baryon densities is that the universe is homogeneous on a large scale of about 250 million light years. So this scale is cosmologically significant, which means we can't simply use uh, classical notions of space, where we simply find volume using radius into pi r cube or something like that. The finding the region of space is a bit non-trivial, but we expect, and by theory, we expect that the universe is homogeneous on a large scale, which means the baryon density shouldn't vary for these large-scale areas. That's why we say we expect the omega b value for the low-Z universe to be similar or close to the one we found earlier, which is this. And the first one of the techniques used to find baryonic matter is the Lyman Alpha forest. And what the Lyman Alpha forest basically means is, consider this very distant object which is emitting radiation. This is probably an accreting black hole or a quasar, something like that. And then it emits UV rays or X rays, basically energy, basically light of very low wavelength. But then it passes through all of these gas, which possibly contain atomic hydrogen. And atomic hydrogen, so this Lyman alpha absorption line is at 121 nanometers, as we know, it responds to the n is equal to 1 to n is equal to 2 transition. So what happens is some of the light is absorbed, and so what you see is at here you have this absorption feature. But also, since it is so far away, it is also redshifting as it gets towards us. And so every time there's an absorption peak, the point of the peak is a bit different, because by the time it has gone from this dust, the photon, like the light has gone from this dust patch to this dust patch, it has been redshifted to a decent extent. And that's why when you see the spectrum, what we see is, instead of just one huge absorption feature, we have a Lyman Alpha forest because you have multiple absorption features across a huge, uh, because of the redshift, you have this huge spread of the absorption lines. And these absorption lines are used, and these intensities of absorption lines are used to calculate how much baryonic matter has passed through. And based on that, we can estimate how much matter is there in between these two points, that is between the distant source and us. And the Lyman alpha forest basically traces atomic hydrogen gas, but we can use techniques like this to find other components as well. That we can also use absorption lines of oxygen. One of the common ones is oxygen 6, and this absorption line is also used in a similar fashion. And so you have multiple absorption lines which are used as tracers of gas tracers, and this helps us in finding what the baryonic content is across the line of sight. What it also quantifies matter in the warm hot intergalactic medium. So getting to what that is, so the warm hot intergalactic medium. So these are some couple of hydrodynamical simulations, and this one is about the cosmic web, or the filaments of the cosmic web. And so you have regions of space which are very hot and or cold. And so based on these hydrodynamical simulations, we predict that certain regions of space would have very hot matter. And so the prediction or current understanding is that the warm hot intergalactic medium is a sparse warm to hot plasma that is believed to exist in the spaces between galaxies. And it contains about 40 to 50% of the baryonic matter of the low-Z universe. So we expect the warm hot intergalactic medium to solve the 30% missing baryonic content. So the problem is finding this WIM is a bit hard, WHIM. And so there are multiple techniques to find this WHIM. And so one of the techniques used is that you have a distant X-ray source, and this distant X-ray source comes through the warm hot intergalactic medium, and then you have absorption features, and based on your absorption features, you can quantify the amount of material in this warm hot intergalactic medium. And another example is highly ionized oxygen atoms showing absorption features in this region, warm hot intergalactic medium region. And these are just a couple of techniques. And over the years, over multiple research papers, it has been seen that it keeps adding up, and you have the baryonic matter is still there to be found possibly. And in 2020, this paper came out, which claimed, or in fact, it is now accepted to be a proper census of baryons in the universe. And what it does is that it found the missing baryon based on fast radio bursts. So what are fast radio bursts? Fast radio bursts are basically, so let's say we have this distant source. We don't actually know what the source of the fast radio burst is, but what we do get is that we get this a very intense radio wave in a very short amount of time, and it passes through a lot of gas, which could be interstellar gas or could be the WIM as well, and then it reaches us. So this very intense and very brief radio wave is called fast radio burst. And this paper used about four fast radio bursts uh, to quantify the amount of baryonic matter present in the WHIM, and by adding with existing values and comparing all of the values from different papers, they were able to find a baryon density parameter of about 0.051, with errors, of course, with a plus or minus about 0.002, if I'm not wrong. But essentially, what they were able to find is that they did find all the missing baryons by considering these four fast radio bursts. And how it works is that when the radio burst travels through the WIM, each baryon or each electron it passes through, each baryon or electron passes through has an imprint on the radio wave, and that is observed in the spectrum. And using that, we find an estimate of the electron column density. And with this electron column density, we can find the amount of baryonic matter present. And that is what, and the calculations are a lot more rigorous, of course, and I haven't mentioned them completely in these slides, but they were able to achieve and find a baryon density parameter of about 0.05, and this was in 2020. Since then, multiple researchers have been working to find or confirm the existence of the WIM, confirm if that in fact had all the missing baryons, and to confirm that, researchers are using something called the Zella effect, which is the spectral distortion of the CMB radiation through inverse Compton scattering. What it means is that the CMB radiation we get, as I mentioned earlier, it has a lot of anisotropies, and and these anisotropies are because it passes through a lot of matter, and even though it started off in a very early time of the universe, due to the expansion of space, due to cosmological expansion of space, it has still passed through a lot, or has interacted with a lot of electrons of baryonic matter, and because of that, you have all these anisotropies and minor anomalies, I may call it. And based on these, we are able to estimate whether baryons are there or whether electrons are there. We are able to identify free electrons of baryons in intergalactic medium or interstellar medium. Specifically, the Zella effect is good in identifying dense clusters of galaxies, and it is also independent of redshift. And I cannot elaborate more on this because I will provide a source for this because sort of complicated. And but the Zella effect is useful in finding the amount of baryons as well. And currently, what people are trying to do is to confirm this value that we got from the fast radio burst and confirm if the WHIM is in fact the source of all the missing baryons that we wanted to find. And that's about it. So the further observations would help in reducing the error limit because currently, as I mentioned earlier in the Planck collaboration values even here, the error estimations here are very, very low. So you have comparative order is about 10 power minus 3. So, and the density parameter found over here, 0.051, the order of error is not, there is a considerable amount of uncertainty, and that is simply because finding or estimating all of these masses of these gases is not easy. And because of that, to reduce the uncertainty, people are trying to use the Sunday effect and look into more matter and look into more observations at the low Z universe, so that we can make a complete picture of how the low Z universe compares with the high Z universe. That's about it. Although I think I finished it in 15 minutes. How long has it been? Hello. Oh, can you hear me?
Yeah, we can hear you.
Yeah.
Can you go back to the
Can
you go back to the cosmological parameter part?
Yeah.
The density. So the calculation of the baryon density parameter, and I mean, I don't know cosmology, like, I mean, obviously, but how rigorous is this calculation? How did they exactly get this? I mean, no need to get in detail, but
So the Planck data, so from the CMB radiation, so that I mentioned, so they have the the CMB spectrum, and from the whole spectrum, what they do is, from what I read, they take the spectrum, and the problem is, all in this map you see that it is spread out across the whole thing, and and what happens is you have to account for the spatial distribution as well. And to account for the spatial distribution, they use a couple of techniques, which maybe I can go. Okay, so in the Planck paper, what they did was from the power spectrum, they were able to, they had, I mean, it's honestly a bit complicated. And since I did not understand the whole thing from cosmology, I was only able to give a brief outline. And perhaps I can look into it a little more and answer your question.
Okay. Good.
I mean, the discussion is a bit, probably a bit quicker, a lot quicker, simply because there is a lot of theory behind how we find all these parameters in this Planck model. And this whole paper is about 60, 70 pages. It uses quite a bit of cosmology. And I was able to go through it, but for the public talk, I wasn't sure if it was
What
easy
is
to explain.
what is the Big Bang nucleosynthesis again?
Oh, the Big Bang nucleosynthesis model. So, the
I
Big
mean,
Bang
just the
nucleosynthesis.
formation of the first particles, right?
Yeah, yeah.
Is it?
So it's based on cosmic abundances. What they do is they set up a couple of initial conditions, and then they perform some hydrodynamic simulations, and then they predict how much baryonic matter would be there, something along those lines. From there,
It's a
they were able to find a similar baryonic parameter.
it's a simulated visualization of the Big Bang or something.
Uh, it's somewhat similar to hydrodynamical simulation with the initial constraints, and they have to uh,
Oh.
based on that they found another gamma b value. I mean multiple parameters, but yeah, the gamma b value is what we are talking about here.
Good, good. And all of these things are in extreme detail, so it's hard to get the full feeling.
Yeah, yeah. The main part about this talk is honestly the paradox is that we were not able to find it earlier, but once we do look at the whole WHIM, we are able to find all the missing variants. So that is essentially the outline of the talk. That is the paradox is sort of solved in code, but with just not enough rigor with respect to uncertainty.
Can you hear me?
Yeah, yeah.
About the fast radio bursts, how did they estimate the electron column density? Because in other places they've used absorption features and those sort of things. So how are they using absorption features or something for the
I mean,
radio wave?
electron. Yeah, it's not absorption features. I believe it's something similar to the Zella effect where you have inverse Compton scattering. They're measuring the scattering. They are measuring how much energy is lost based on that scattering. They're able to estimate how many electrons are there, and they're able to find an amount of electron column density. I believe it's mostly due to Bremsstrahlung radiation and how much it's something along those lines.
Okay, that sounds cool. Thanks.
Yeah, so can you hear me?
Yeah.
So might be a slight digression, but when talking about all the missing baryon problem, how much of it was actually solved in quotes from the observational data versus how much motivation could they take from the standard model itself?
Could you phrase the question?
Okay, so when they were, as they were trying to, probably in this paper itself or in the other one that you spoke about, how much of it, how much of the problem did they address using this versus maybe taking theory from the standard model, or did they involve any beyond the standard model approaches?
No, I mean this faster universe was just to cover the 30% missing baryon, and before that we were able to find, like as I said from here, this even in this paper they were able to estimate the rest of the 70%. Is that what you're asking?
Yeah, so is this part theoretical or simulated?
This one, all these are observational data. Like
Okay.
Yeah, so all these are observational data because so you have here the WIM as well. Here you have the O6 absorption. From there, they're able to get 17%. And this one's from the Lyman Alpha forest of the WHIM, and this was Lyman Alpha forest of other gas. And so all these are observational data. These are not from simulations. These are actual data from multiple archives, and they were able to estimate this much. The only reason this was missing because not the whole WHIM was not covered. That's why you have this. You had this 30% missing.
Okay. Yeah, thanks.
Any other questions? If there are no other questions, I can stop presenting for my part. All right, okay, since we don't have questions, we'll have to wrap it up. Apologies for making it a very short presentation. I hope to send a few articles if you are interested. And that's about it. Thank you for coming.